In this module, you will learn to solve linear programming problems. Let us recall the graphical solution of a linear inequality. Given a linear inequality, x plus y less than 6, its solution can be found graphically by first drawing the graph of the equation x plus y is equal to 6, and then consider an arbitrary point that is not on the line. For example, the origin, if it satisfies the linear inequality. Then the solution region is towards the origin, else it is to the other side of the line. To find the solution of the system of linear inequalities, we draw the graphs of the inequalities in the same manner and find the common region. The common region of the solution of the inequalities is the solution of the system. Now, let us apply the graphical method of linear inequalities to solve linear programming problems. Let's take a look at one problem. In this problem, a manufacturer produces two different models of a product and wishes to maximize his profit under some given conditions. Such type of problems, which seek to maximize or minimize profit on cost, form a general class of problems called optimization problems. The special type of optimization problems is linear programming problems. Linear programming problems involve the optimization of a profit or cost subject to certain overriding conditions or constraints. There are several methods to solve a linear programming problem, but in this chapter, we will learn only the graphical method. Let us now frame the inequalities in terms of x and y. In this problem, the number of units cannot be negative. Hence, x and y are greater than or equal to 0. Machine 1 takes 1 hour to complete 1 unit of model A and 4 hours to complete 1 unit of model B. Therefore, the time taken by machine 1 to make 1 unit of both the models is equal to 1 into x plus 4 into y hours. Now, machine 1 can work for a maximum of 8 hours. Therefore, the linear constraint is x plus 4y is less than or equal to 8. Given that the second machine is used for 2 hours to complete 1 unit of model A and 2 hours to complete 1 unit of model B, and it cannot be used for more than 10 hours, it implies that 2x plus 2y is less than or equal to 10. This can be simplified to x plus y is less than or equal to 5. It is given that the profit on model A is Rs 100 and on model B is Rs 200. And hence, the total profit is 100x plus 200y. This is the objective function. The manufacturer wants to earn the maximum possible profit. This can be attained by maximizing the objective function. Mathematically, a linear function z is equal to ax plus by, where a, b are constants and which has to be maximized or minimized, subject to constraints in the form of linear inequalities, is called a linear objective function. Let us now solve the linear programming problem using graph. Obviously, x greater than or equal to 0 and y greater than or equal to 0 have the solution in the first quadrant. the solution of the inequality x plus 4y is less than or equal to 8 is the shaded region as shown. The solution of the inequality x plus y is less than or equal to 5 is towards the origin. The common region of all these inequalities is known as the feasible region or feasible solution. To maximize or minimize the objective function, we use two theorems. The first theorem is, if R is the feasible region for a linear programming problem and Z is the objective function, then the maximum value or minimum value of the objective function must occur at the corner point of the feasible region when it is a closed or bounded region. The second theorem is, if the feasible region is open or unbounded, then the maximum or minimum value of the objective function may not exist. If it exists, it occurs at a corner point of R. When the feasible region is closed, let P and Q be the maximum and the minimum values of the objective function. If the feasible region is open, we have two cases. Case 1. If the open half plane determined by ax plus by greater than P has no point in common with the feasible region, then P is the maximum value of the objective function. Else, there is no maximum value. If the open half plane determined by ax plus by is less than Q has no point in common with the feasible region, then Q is the minimum value of the objective function. Else, there is no minimum value. This method of finding the maximum or minimum value of an objective function is known as the corner point method. Let's come back to the problem that we were discussing. Here, the feasible region is a closed region. The corner points are O, 0, 0, A, 5, 0, B, 4, 1, and C, 0, 2. As per Theorem 1, the objective should be maximized using the corner points of the shaded region. Let us substitute the corner points in the objective function. The value of the objective function is 0 at the origin, 500 at A, 5, 0, 600 at B, 4, 1, and 400 at C, 0, 2. The maximum value of the objective function is 600, which occurs at B, 4, 1. Hence, 4 units of model A and 1 unit of model B should be made so that the profit is maximum.